All right, so today we're going to talk about polar versus nonpolar molecules. And this is different than polar versus nonpolar bonds, so please be careful and don't confuse the two. Bonds, when we're talking about polar versus nonpolar bonds, we're just talking about how well two elements share electrons, who's going to have the electrons more often. When we're talking about polar versus nonpolar molecules, we're looking at how the electrons are behaving all the way around the molecules. So in this case, like I've got this tetrahedral here, and we're going to be thinking about how the whole thing, does it have any partial positive or partial negative parts to it. So it's a little bit different than the polar and nonpolar bonds. Just make sure on a test or a quiz you are reading the questions carefully and using the correct thought process to solve the question and get the right answer. So the first thing up is going to be the nonpolar molecule. And these aren't going to make a whole lot of sense right now. I just need you to bear with me and follow through. I promise we'll get you where we're going. So nonpolar molecule is a molecule in which the electrical charges are distributed evenly across the molecule. Okay, and an example we're going to write down, and we're not going to really talk about it just yet, is CO2. So carbon dioxide is a good example of a nonpolar molecule. We'll come back to that in a minute about why. All right, the next thing is just kind of the opposite of that, and I'm sure you guys could come up with your own definition based on the one above and figure out how we're going to define a polar molecule. Okay, so the key word in the first definition was distributed evenly. So obviously in a polar molecule, that's not going to be the case. So it is a molecule with an uneven distribution of electrical charge. So that means we're not going to have everything's all hunky-dory where all of these guys kind of have the same electron situation on the outside. So there's not really a difference between each side. We're obviously going to have an area of the molecule that gets more electrons than the other part of the molecule, and therefore it's going to leave it a little bit wonky. All right, so this uneven distribution results in a region of higher electron density and so that is going to give us a partial negative charge. Okay. So if I've got a whole bunch more electrons located in an area, overall that's going to give me a partially negatively charged area. It's also going to result in a region, so if I have more in one area, that means I'm going to have less in the other. So a region of lower electron density, or a partial positive charge. I know that in the beginning this is a bunch of words and it doesn't necessarily make a whole lot of sense, but it does come pretty quickly for most students, so I think you'll be okay, even if you're not fully understanding it right now. All right, so the partial negative and we have a symbol for that, just like we did with the bonds. Okay, let S with a negative symbol. and the partial positive regions create what is called a net dipole moment. Or a permanent dipole. Okay, those are kind of synonymous terms. Okay, so an example of a polar molecule would be water. Okay, again, we'll talk more specifically in a minute about how that's true, but basically I can tell you now that CO2 has no area of the molecule that has an uneven charge distribution, and we know that water does have an unequal charge distribution. And so now we're going to talk about why. Okay, so how can we tell? Well, if something is polar or nonpolar, right? So the first thing you can look at is the terminal atoms. If they do not match, it is polar. You get to stop. That's easy breezy. So if I have something like HCN, so if I have something like that, I have two terminal atoms that do not match, so this is automatically polar. All right, the next one, if they all do match, so if the terminal atoms match, we have to look at the symmetry of the molecule. Now, I'm going to tell you, we're going to explain why that is in a minute. So right now you still don't have an answer as to why, but we will talk about that. So let's go on. So still under number 2, so if you've already on another page or something, we're going to be indenting from number 2. So under number 2, we have if the molecule, if the molecule is symmetrical. It is nonpolar. Remember, this is under the if all the terminal atoms match, okay? The other scenario you would have is if the molecule is asymmetrical. It is polar. So we're going to learn about that here in a little bit, how to determine if it's symmetrical or asymmetrical. But I need to talk to you about why, okay? So the important part is you're in CAP, and we need to know and understand why. So, but why is that true, okay? And now we get into a little bit of a higher end thing here, but it's really not that difficult once you get through it. So we're going to go back to that first example. Remember we said that CO2, I told you was nonpolar. So let's take a look. And if I have, y'all know how to draw CO2, so I'm not going to take the time to draw it, like explain the drawing. All right, so we have our carbon dioxide molecule right there. I'm going to do CO2. Okay, so in this case, we know that the oxygen is more electronegative. Doesn't matter how much more, it is more electronegative. So oxygen is more electronegative, therefore, those three dots right there in shorthand means therefore, the pull of the electron, or the electrons, is toward the oxygens. Okay, it is toward the oxygens. All right, so let's go ahead and draw that on our drawing. So we have the arrow heading toward the more electronegative atom, and this arrow heading toward the more electronegative atom. Because these terminal atoms match and they are the same, the difference in electronegativity between the C and the O is the same on both sides. So that pull is going to be the same. So the pull is equal and opposite. So the pull is equal and opposite, so they cancel out. Those forces cancel out. All right, so I want you to think about tug of war. So all the time in these, think about electronegativity as kind of like tug of war. So in this case, I have two equally matched teams because they match, right? They're both oxygens. And they are pulling, and y'all have seen tug of war before, when the two teams are really evenly matched, nobody moves, nothing moves. Okay, the forces are pulling in equal and opposite direction, so there is no net force acting on this. And so, because these forces cancel out, there is not a net dipole moment. There's no permanent dipole. Right? So that's it. Now we know, because those forces cancel out, we can now say, and we know for a fact, this is non-polar. It is a non-polar molecule. All right. Now, moving on to our other example that we had, which was water. Okay, again, you know how to draw water by now. You should be able to do it in your sleep. We have this going on. All right. So, with our water, again, the oxygen is the more electronegative atom. We automatically know we're going to have a pulling of electrons there. Okay, and they are going to pull toward the oxygen. All right. So this is where we need to really be critical thinkers. So I'm going to move these arrows. I'm just going to move them over here so we don't have everything else on the picture. Okay. So I've got one arrow going one direction, the other arrow going the other direction. All right. So you should be able to see there that with the naked eye and not having ever taken physics or anything like that, you can see that these are pulling in opposite directions in terms of left and right. I think we can agree on that. This one's going to the right, this one's going to the left. Okay? But we also can agree that both of these arrows are going upward. Okay? And so they can't cancel each other out, right? Because there's no force. If both forces are going upward, then there's nothing pulling in the other direction to cancel that force out. And so another way to look at it, for those of you who this would make more sense, and if this would make sense to you, then that is okay. Just follow along and try to follow. So if I'm moving in this direction, I have a little bit of movement on my x-axis, and I have a little bit of movement on my y-axis. Okay? Same thing here. I have a little bit of movement on my x and a little bit of movement on my y. Okay? So these two on the bottom are going to be equal and opposite. They're on the same plane, and they are going opposite directions. They cancel out. Okay? But let's look, I'm just going to draw them by themselves down here. So these guys here cancel. All right. But however, these guys that are going up, okay, when you're doing this in physics, you actually add these together, okay, because the force is twice as strong. We have this force pulling and this force pulling. So what you end up with is this dipole. I'm going to use this color right here. So the net force that's acting, remember these forces have canceled each other out. So the net force that's acting is going through the molecule in this direction permanently. It's always going to be there, okay? And so this is your net dipole, or your permanent. Okay, and we need to give our partial positive and partial negative charges. So if this is the area, oh, sorry, I need to put my little thing here. Okay, so if this is the direction it's moving, we know that goes toward the more electronegative atom. So what it does is it means that this end of the molecule, that region of the molecule, is going to have a partial negative charge. And this region, this whole region on the bottom, is going to have a partial positive end. Okay, so this molecule is not evenly distributing its charges. Okay, again, this is our 3D version of it. We've got our water molecule here. We have a force going this direction and a force going this direction. We have nothing counterbalancing it going the other direction. Therefore, the net force is going straight up through that molecule. And that means that this region of the molecule is almost always negatively charged. That's why it's a partial negative. It's almost always negatively charged. And this region is almost always partially positive. The reason I say almost always is because the electrons are always traveling. So they may go take 6 laps around the oxygen and then 1 lap around a hydrogen, and then 6 laps around the oxygen and then 1 lap around the other hydrogen. So it leaves this area without the negative charge and has more negative charge up here. All right. So let's write ourselves a little note. The net dipole indicates that oxygen, or say the region around the oxygen, will have electrons. Therefore, there's my little therefore symbol again, a partial negative charge. And the hydrogen regions will have fewer electrons. Therefore, it will have a partial positive charge. All right, so now that we've determined that these do not cancel each other out, okay, now we know if they don't cancel, it's going to be polar. It is a polar molecule. Now, are you going to have to do these drawings all the time? No, absolutely not. If that helps you, I say go for it, because once you get into college and things like that, you are going to do that a lot more often. But I have another video, and I'll talk a little bit about at the end of this video about how to recognize whether it is going to be an asymmetrical or symmetrical shape. Because remember, that's what this comes back to, is asymmetrical or symmetrical. When I'm talking about symmetry, I'm talking about, do we have a force acting in the same direction, canceling each other out all over the molecule, or do we not? Let's do 2 more quick examples. So the first one we're going to do is BF3. Okay, so again, we all know how to draw this by now. I don't have much time doing that. All right, so I've got BF3. Let's draw our vectors, or our dipoles. So we know fluorine is more electronegative than boron. So every one of these is going to go this direction. Okay, this is one that students struggle with. Trigonal planar is hard for kids to understand because you think, oh, well, two are pulling down and only one is pulling up. But remember, there's no top or bottom to this, okay? It doesn't matter how I rotate it, okay? They are going to be exactly 120 degrees apart from each other. So you can think of it as three people playing tug of war, and I have an object in the middle. If we stand exactly 120 degrees apart from each other, and we pull with the exact same force, this object in the middle will not move. Okay, so therefore, nobody is able to overpower anybody else. It'll be a stalemate. So therefore, it's the same thing with electrons. They are going to be evenly distributed throughout this one. I'll show you the vector addition. It's a little bit different for this one. It's not quite as easy to see and like recognize. But what you do is you pull out again your three forces working here, and we're going to see if they will cancel each other out. So we have this one going this direction. That's that one. This one would be the same length. And please forgive me if I don't draw a perfect equilateral triangle. This one would be the same length. And this one would be the same length. Okay? And they all end up canceling each other through this process. So as long as you have the same terminal atoms, then you're going to end up canceling these vectors. So trigonal planar is probably the hardest one for kids to understand because it just seems it's a little bit hard to wrap your mind around. Speaking of that, let's do the next one. Okay, one more example. So this one is nonpolar. I'm sorry, polar. Sorry, nonpolar. I can't talk. It's late in the afternoon. This is a nonpolar molecule. All right, and the last example we're going to do is going to be NH3. All right, so this time, again, I'm going to just draw it for the sake of being fast. Okay, so let's talk about those dipoles again. Nitrogen is more electronegative than hydrogen, so my arrows are going to move inward. The pool is going to be equal on each of those. And let's take a look at the three-dimensional, our little ball and stick model. Okay, so in this case, we have got, if you look at it in 3 dimensions, every one of these would be pulling in the upward motion. Okay, yes, there's some amount of canceling because they're going in different directions, but every single one of them is going up. And so you will have to understand and see that eventually what's going to happen is if you added them all up, they're all going to go, all 3 added together is going to go straight up, just like with the water molecule. Because we can cancel the left to right, but we cannot cancel the up. Every single thing is going up, and therefore there's nothing counteracting that to go down. So, again, to draw that dipole, I'm going to draw a nice thick line, be very dramatic about it. Okay, and then I've got, again, to label the overall molecule. So this region of the molecule is going to be partially negative, and this region of the molecule is going to be partially positive. So this is called a polar molecule. Okay, if you're good with that, then you're good. If not, I'm going to do a little bit more, so stick around if you want to see anything else. Let's take a look at, so this we said is nonpolar. But remember, that's a caveat of if all the terminal atoms match. So if I change these out, these were hydrogens, let's say, okay? And I change this out, and one of them is a fluorine. Okay, so let's draw that really quickly. Let's say that this is BFH2. All right, if I've got that, so this is my boron, I've got 2 hydrogens and a fluorine. When you're going to draw these, which again, you don't have to do all this process, it's just for you to kind of understand the why. All right, so I've got hydrogen, hydrogen, and fluorine. So when you look at your dipoles, now look what's happening, okay? Ooh, I don't remember my electronegativity. I don't remember who's more electronegative. on. All right, the hydrogen is more electronegative than the boron, so we're going to have this going here and this going here, okay? And we know the fluorine, because fluorine's more electronegative than everybody. All right, the difference is this is a whole lot more electronegative. So now we don't have the symmetry of the same exact pull on these bonds or on this molecule. So that fluorine is going to be far more electronegative than these two down here. And therefore, my net dipole is going to go toward the fluorine. Okay? So that's how if you have different terminal atoms, that's how that comes into play. Because the terminal atoms will have different electronegativities and different ability to pull. So in this case, we would end up with the fluorine. And it happens to be that every time I draw these, the more electronegatives on the top, but that's not always the case. So don't get lulled into thinking that's always true. So this would be partial negative, and this would be partial positive. Okay, so I have a whole different video that goes through the the symmetry of the molecules and being able to identify if they're symmetrical or asymmetrical. So follow this with that one.